Hi everyone, we're going to start organic chemistry now. So we are going to go with the basics on alkanes, and this will be the start of the material that is covered in exam 2. So when we start talking about organic compounds, remember organic chemistry is the study of carbon-containing compounds. So organic compounds must contain carbon and hydrogen. They also can contain oxygen, sulfur, nitrogen, phosphorus, even some of the halogens, a variety of other things, but the main components need to be carbon and hydrogen. This is why we call them hydrocarbons. Now, there are certain properties of organic compounds that we want to just remember, and that is that they are nonpolar. So they're held together by nonpolar covalent bonds. Because of this, they have low melting points, low boiling points. They're not soluble in water. They're less dense than water, so they'll always float on top. And they are highly flammable. This is just giving you an idea to compare and contrast organic versus inorganic, so you can know the differences in elements, bonding, polarity, their melting points, boiling points, flammability, and then solubility. So if we ask to do this and go through this little learning check and identify as these following characteristics as either inorganic or organic. The first one, a high melting point, is seen in inorganic compounds, so ones that are ionic. If it's not soluble in water, that means it is organic. If the formula is just C's and H's, this would be an organic formula. The formula MgCl2, again, remember here we have an ionic compound, so this would be inorganic. Flammable means we are organic, and nonpolar is another organic characteristic. So hydrocarbons, these consist of carbon and hydrogen atoms. When we draw them, we usually draw them using electron dot formulas. Now, carbons, remember, can have up to 4 bonds. So we have to have 4 bonds on each carbon atom. If we're using single bonds, we could also have double or triple bonds, but we're going to talk about those later on. So in the basic hydrocarbon here, we are saturated when we have all 4 bonds being utilized, okay? If we only have single bonds on the carbon atom, we are therefore considered saturated. Now, when we look at these carbon atoms and we look at the geometry of them, they all have what we call a tetrahedral structure, okay? And they're all 109 degrees apart from each other. So each hydrogen acts as its own little electron repulsion group, and they end up repulsing each other till they're exactly 109 degrees apart from each one, and we have this tetrahedral arrangement. Now, when we add 2 of those carbon-based groups together, now we have ethane here. Before we were looking at methane. Again, we still have that tetrahedral shape, but we can also spin on these axes, which are pretty cool. Now, we're not going to really worry too much about here. What we're going to see a lot are these what we call line bond drawings, and that's what we're going to focus on doing, and condense structural formulas from there. So let's go with the basic names. All of the names of alkanes are determined by the International Union of Pure and Applied Chemistry, so IPAC. What we do is we have a prefix that we use to denote the number of carbons in the chain. So all of our names are named after the longest chain of carbon. We don't really care about what's attached right now. We just care about how long that core carbon chain is. So we use a prefix to determine the amount of them, and then because they're all singly bonded, we end them with ANE. So the prefixes we use are similar and yet different from what we were doing before. Instead of using mono, we use meth. 2 is not di, it's going to be eth. 3 becomes prop. 4 is bute, and then 5 and above are actually the same. Okay, so then we get to the pent, hex, hept, oct, non. So if we're looking at names, if we're looking at the names of these, 1 carbon would be methane, 2 carbons would be ethane, 3 carbons propane, 4 butane. And then these are the molecular formulas. Now remember, these are not the structural formulas. These are just what we do when we condense them down together. So those are the formulas there. Here are the condensed structural formulas. These are how we're really going to see them and draw them. Again, if we're naming them, one is meth. So this would be methane, ethane, propane is number 3, butane, pentane, getting to 6. We're going hexane, heptane, octane, nonane, decane. So I'm going to ask you to work with me, and we are going to name the following ones, and then we're going to draw some. So in this case, the first one is 2 carbons long. This becomes ethane. 3 carbons long is propane. And then let's count the longest chain here. 1, 2, 3, 4, 5, 6. 6 carbons long becomes hexane. If you're asking to draw them, or I will probably ask you to draw a few, I'm going to move this out for us so we can see. And I'm going to hopefully make it a little bigger. So let's get to drawing. We want to draw pentane. The first thing you're going to do is make sure you draw the carbon structures. So we're going to just make a list and draw out the 5, because pentane means 5 carbons and the ane means they're singly bonded together. So we're going to do 1, 2, 3, 4, 5. There's our carbon backbone, okay, for pentane. Now carbon makes 4 bonds each. So we're going to draw the expanded, and then I'm going to show you how to do the condensed afterwards. So in an expanded drawing, we show all the bonds. So we're going to make sure that each carbon makes a total of 4 bonds. So we're filling in the rest. So the carbons on the end, if you notice, have 3 spaces that we need to fill in, and everything in the middle has 2. So now we do, because this is a hydrocarbon and it is just filled with carbons and hydrogens, we're going to saturate this with hydrogens. So all of these bonds will be filled by hydrogens. When we're not going to use hydrogens is when it's noted. So when the name changes at the end, instead of ANE, maybe it's OL, that means there's an alcohol group. Or if we say that there's an attachment somewhere. If that's the case, then we'll say it before. But right now it's just hydrogens, so let's fill them all in. So there's 3 hydrogens on the end, and then 2 for every one in the middle. And then again, 3 on the end. This is the expanded drawing. Now to condense it, we don't show the bonds to the hydrogens, because realistically when we get into like decane or nonane or octane, this is a lot to draw. So we condense them down to make it easier. And we condense all the bonds that are hydrogen based around the carbon. So this one becomes a CH3. This reads that there are 3 hydrogens bonded to this carbon. And then we're showing the bond of another carbon to that, okay? Now we have 2 here, so this becomes CH2, 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 and at the end is CH3. So this is technically the answer that we're going for. This would be pentane. And remember, for pentane, if we're looking at this condensed structural formula, we're showing the bonds between the carbons, but we're not showing the carbon-hydrogen bonds. We're condensing those around each carbon, okay? And this is considered a saturated hydrocarbon because they're all single bonds going together. So this would be expanded, condensed. And just for you on here, those are also the answers. So if we move along, when we started just talking, and I just kind of went over it, but there's a difference between expanded and condensed. In an expanded formula, you show all the bonds. In a condensed, we just show the carbon bonds. We don't show the bonded to actual hydrogens. The other way we can draw and show our carbon bonds are by doing what we call line bond formulas and skeletal formulas. Now, in these, we use them, we just show the lines each here represent a bonded carbon to another carbon. So we're really condensing down, and this is kind of like we call the lazy chemistry way. But when we really get into some carbon-based compounds that might have, especially lipids, that might have 18 or 20 carbons long, that's a lot to constantly write those out. So we just show the carbon-carbon bonds by a line to each other. So wherever you see the end, so a peak or a valley, that is a carbon, okay? And then it is considered saturated with hydrogens. So if we're looking at this bond here and we're counting it, I'm going to recreate it up here as we go. So if we're looking at the one on the bottom, okay, we're just going to count through. Technically, this is a carbon, so 1, 2, 3, 4, 5, 6, 7. There are 7 carbons in this. This means this would be heptane. Okay, that's the skeletal formula, a zigzag pattern. What's really saying is this is a carbon here, here's a carbon, this is carbon, this is carbon, this is carbon, this is carbon, and this is a carbon. Now, it's up to you to assume that this is saturated, so that on the ends, these are technically CH3s, and everything in the middles are all CH2s. So you could realistically, if we're doing the expanded one, draw in everything. And if we're going, oh my goodness, I'm going to get a hand cramp here, drawing in all those hydrogens. So this is why we really just use the lines, okay? Getting sloppy otherwise. If you wanted to do the condensed structural formula of this, it would be CH3, CH2, 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 and then CH3, okay? So this is sometimes where we'll just condense it even further and just show the carbon-carbon bonds. So again, here we go. This is a ball and stick molecule, expanded, condensed, and then skeletal, back and forth. What's really neat is that we can actually rotate around these carbon bonds. And so the groups that are attached to a carbon-carbon single bond can actually spin and move, and they can move freely. There's nothing that's stuck in place, holding it in place. We can kind of rotate it around like it's a little wheel. And because of that, we can get what we call conformations. Now, conformations are just different ways of drawing the same molecule. They're just different structural arrangements. So sometimes some will be up and some will be down. And we're going to kind of go over that next right here. So here is butane. Butane just has 4 carbons together. However, I could draw the condensed structural formula in a variety of ways. The main thing here, what's most important, is that it's just the longest chain of carbon that dictates the name. So as much as you might want to say, oh look, Melanie, this must be ethane with two groups attached, or this must be propane with 1 group attached. Technically, these are all the same. It's the longest continuous chain of carbon. This is still 4 carbons connected, 4 carbons, 4 carbons. So you can see there's a variety of ways to draw it. But either way they're drawn, they're all the same. These are all butane molecules. So these are considered conformations, okay? When we draw these structural formulas in a condensed structural formula, just remember on the ends we usually always have CH3s, and in the middle we usually write CH2s. And if we're doing it as a skeletal formula, the ends and corners always represent carbon atoms, and we're going to zigzag up and down. Okay, so each peak and each value represents a carbon. So this is how you would do taking an expanded formula. Here is 1, 2, 3, 4, 5. This would be pentane. We could condense it down, and then you could even condense it further to the skeletal formula. And here 1, 2, 3, 4, 5 carbons long, pentane. So let's look and do this one now. I'm going to ask you to draw the condensed structural formula here, and then we're going to go from there. What is its molecular formula and what's its name? So condensed structural formula wise, I'm just going to put my thing over up top. Just remember these are hydrogens I covered up in this, or maybe I'll move this lower. Here we go. We'll put it a little lower here. Let's condense these down. So let's do the end first. The end condenses down to a CH3. Then we have a CH2, CH2, another CH2, one more CH2, and then a CH3. The molecular formula, okay, when we're drawing the condensed structure is what we did here. The molecular formula for this is if we add everything and total it all together. It doesn't show us any structure whatsoever. It just shows us the total number of atoms. That's all a molecular formula does. So in this case, let's count them up. 1, 2, 3, 4, 5, 6. So it becomes C6. And then if we're going further, we're going to count how many hydrogens. So here we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6H14, this would be what we call the molecular formula. And now we're going to get into what the name is. So the name here for anything that is 6 carbons long is hex. And because it is all single bonds, this becomes ANE. Hexane is the name. So let's draw some more. We're going to just constantly get into naming and drawing, just so you get the pattern down. And the reason why we're trying to get these patterns down, if you can understand this, this is the biggest battle in organic chemistry because we're going to just add on from here. Okay, so let's draw the condensed structural formulas for the following names. We have ethane and heptane. So for the first one, for A is heptane. Excuse me, ethane. In ethane, eth means 2. Ane equals single bonds. So we're going to go 1, 2 together. And then you would just have to fill them in. Because they're both ends, this is basically going to be a CH3, CH3. If we're doing expanded again, remember 4 bonds. Then you'd fill them in, H, 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 H. Another hydrogen there. Condensed is just CH3, CH3. Okay, that is ethane. For number B, or letter B is heptane. Hept means 7. Now we're going to draw 7 across. 1, 2, 3, 4, 5, 6, 7. So as we have our 7 here, remember anything on the ends are CH3s. Everything in the middle are CH2s. The only time we'll ever change this and have something other than an H and have nothing different than 2 is if we have something else coming between it, okay? So heptane and ethane. To complicate things even further, we can have what we call cycloalkanes. In this case, they are a carbon-based ring. So we can actually, instead of forming a line, we're going to connect them all together. They have 2 fewer hydrogen atoms than a straight chain alkane, and they have the same number of carbon atoms. And because of this, we use an extra prefix that comes in front, which will be cyclo. And the cyclo means that they're connected together, okay? So this would be like cyclopropane. So you can have to do these from 3 and above. You couldn't do them anything less than 2 because you can't connect 2 together to make a circle. So let's go through them. Here we have cyclopropane, cyclobutane, cyclopentane, and cyclohexane. And if you're drawing the skeletal formulas, propane looks like a triangle, butane looks like a square, pentane looks like a pentagon, and hexane looks like a hexagon. But if I asked you right now to just go through, this is testosterone, and it contains 5 carbon-based rings. I want you to name each of what we call the cycloalkanes found in this molecule. So here's the biggie. Here's one right here. Okay, it's all single bonds. This one is 5, so this becomes cyclopentane. Then you have 2 that have 6. These are cyclohexanes. As much as we want to call this cyclohexane, it's really close. It has a double bond. Because it has a double bond, this is going to be considered cyclohexene, and we'll get into that in the next group, okay? This is an alkene. The other ones are all alkanes. So let's go through naming as we can name and go from. The first one here, 1, 2, 3, 4, as a straight chain is just butane. The next one here, because this is cyclic, 1, 2, 3, 4 connected together, this now becomes cyclobutane. Here, let's count the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. And in D, 1, 2, 3, 4, 5, 6, but they're all connected together. This is cyclohexane. So there they are for the names. Now we're going to get into some of the harder parts, and the harder parts are when we talk about having what we call substituents or branches. These are things coming off of the actual chain, some form of another group. It could be a halogen that's going to replace the H, or it could be another carbon-based group. Okay, so it's something attached to the carbon chain. Now, because of this, we can actually get into what we call structural isomers. And structural isomers are when we have 2 compounds that have the same molecular formula, so the same total numbers of carbons and hydrogens, but they have different structural arrangements. And those different structural arrangements mean that they result in different names. So now these aren't the same as conformations, they're slightly different. So I want to get into the one talking about butane with you here. So if I look at butane, so here's butane by itself, CH3, CH2, CH2, CH3. This is butane. If we wanted to write the molecular formula for butane, remember it's C4H, and then let's count the H's. So we have 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. C4H10, this is going to be our molecular formula. Now what we want to do is we want to see if we can draw any we call structural isomers from this. So we're going to pop them and move them. If I just move this one up here, and I went like this and said, oh, I'm going to put a CH2 here and I'll put a CH3 up here. And then I'll do a CH2 and a CH3. This is still the longest chain, 1, 2, 3, 4. This is still butane. These 2 things are what we call conformations, okay? Conformations of each other. However, if I did take one off the end, but I moved it to be in the middle, okay? So I didn't move it to here, but I moved it to this position here and redrew it. So now I have 1, 2, I'm going to have 3 carbons like this, but I put one in the center instead. So I arranged my 4 carbons differently. Remember, anything on the ends are always CH3s. Anything in the middle would be a CH2, except that now one of the H's is taken up by this carbon. So this only becomes CH, okay? So it has 1 less to make the bond. If I looked over here and looked at the molecular formula, 1, 2, 3, 4, it's still C4, and H3, 3 is 9, and 1 is 10. It's still C4H10. So the molecular formula is still the same as butane, but my longest chain, no matter which way I go, is 3. So this name is actually propane. But it's slightly different. It's not just any propane, because it has this group here. And when we have this, this here is known as the branch. or the substituent group, we have to denote what it is and where its position is. So over here, it's on carbon 2. So if I start counting from an end, I want to count on the end that gets me closest to the branch. In this case, it doesn't matter. 1, 2, 3. So on carbon 2, I have this group. And this actually becomes what we call 2-methyl-propane. Okay? And now this one here, and butane, are considered to be structural isomers. I know that seems a lot right now, and we'll go through another one, so it won't be too bad. But just remember here, structural isomers are the same numbers of carbons and hydrogens, just arranged differently. The same molecular formula, different structural arrangements. And in this case, if we looked at pentane, I can have pentane by itself, or here I could have a 2-methylbutane or a 2,2-dimethylpropane if we're going off of names. This just shows you the number of structural isomers that are available. There are none for methane, ethane, and propane, but the minute we get to 4, 5, 6, 7, 8, and we're going up to 10, for decane, there are a total of 75 structural isomers that we can make of it. It becomes exponential, okay? The more and more carbons we get, the more and more possibilities we can have for structures. But what do I want you to know? I want you to know actually how to name and understand these groups. So these substituents or branches. Anytime we have a branch that are carbon-based, we're going to call these alkyl groups. So the first one, if it just has one carbon, it's a methyl group, okay? We basically take the alkane name of what it would be, and we drop the ANE and add YL. So hence, instead of alkane here, this becomes alkyl. So this one would be methyl. 2 will be ethyl. 3 will be propyl. I will not ask you any groups of 4 and up. So you only have to know these 3. These are the 3 biggies: methyl, ethyl, propyl. The other common names that we're going to talk are going to be halogens. So they have to be anything in group 7 can make a single bond. So these are going to be our replacements here. So we're either going to be a carbon-based alkyl group, or we'll be what we call a halogen group, and those are halo groups, H-A-L-O, okay, for the halogens. So in this case, we're basically taking the beginning of the name and adding an O, okay, for halogen. So here, fluorine becomes fluoro, chlorine becomes chloro, bromine becomes bromo, and now iodine becomes iodo. Those are the group names. So you need to know these, and you definitely need to know these 3. So there's not too many, you only need to know 7 of what the common names are known as. So methyl, ethyl, propyl, and then we'll go from there. So if we're gonna name them and draw them, the biggest thing when we name is you have to count the longest chain of carbon, continuous chain of carbon. That becomes the base name. We name that as its alkane name. And then what we need to do is start numbering those carbons, and we're going to number it on the carbon end that is closest to a substituent. Okay, so whatever's going to get us our lowest number of substituents, that's the side that we're going to start counting from. And then we're going to give the location using a number, and then the name of each substituent. But we're going to do it in alphabetical order. Okay, that's the big thing, alphabetical order. So if we start doing this one, here's the biggest thing. Let's count the longest continuous chain. 1, 2, 3, 4, 5. Don't forget it bends down, okay? Or here, 1, 2, 3, 4, 5. Either way, our longest chain is 5. So that means our base name is pentane, okay? Now we're going to start numbering these, and we want to start numbering so that we get to this branch point, and this one is the lowest number. So if we went on this side, 1, 2, this is at 2 versus 1, 2, 3, 4. So we want to start numbering here because the branches have to be low numbers. So 1, 2, okay? So now this becomes a 2, position 2, but this is a CH3, that's a methyl group, so 2-methylpentane would be the name. So we numbered them, we know that it's a methyl, and now we can name it as a 2-methylpentane. Here are just some examples. In this case here, 1, 2, 3, this is propane. Now, we're not going to just call this a methylpropane, and I apologize, I forgot to put in there, this should be a 2-methylpropane, because we could actually, so 2-methylpropane. You don't want to have it on a 1, so 2-methylpropane. We can't technically have it on the 1, because then we would literally just have butane. So a methylpropane is the same as a 2-methylpropane, but that's why we have it and not have it there, but I should have it there. And I'll ask you to put them in. In this case here, 1, 2, 3, 4, 5 is the longest chain. This is pentane. Now we have 2 methyl groups, one located at 2 and the other located at 4. So this becomes a position 2, position 4, di, meaning we have 2 of the same, methylpentane. If I had a third one in here in the middle, I would number it as a 2, 3, 4, and instead of di now, I'd use trimethylpentane. Okay, don't get caught up on this di here. Taking apart these names, that di just means that there are 2 methyl groups and they're located at positions 2 and 4. Okay. So what do we want to name these overall? We're going to name when halogens replace a hydrogen. We're just going to, again, number them, do the same thing we did, or we're going to name the longest chain, and then we're going to basically number the carbons, so whichever, whether it be an alkyl group or a halo group, we're going to number so one of those substituents or branches comes first, wherever it's closest, so they have the lowest numbers, and then we'll name them from there. Okay, so if we're naming here, what is the IPAC name of this? Let's go through the longest chain. 1, 2, 3, 4, 5. Pentane is the longest chain here. However, we have to pay attention. We're not going to number from this side because that means I get to a group at 3 versus 1, 2. So we're going to start numbering from this side. So this now becomes carbon 1, 2, and carbon 3. So let's be making some notes. I'm going to open this up so you can see some notes up ahead. So right now we know on carbon 2 we have a methyl, and on carbon 3 we have a chloro. So it's okay. And we have 5, so we know it's a pentane molecule. So we'll write the things that we know. So we're writing the longest name, and then we're writing the groups, the substituents that are there, and then we're going to put this together. So the big thing we have to do now is we have to list our substituents in alphabetical order. That comes first. Well, C comes before M. So even though that methyl comes lower in number, chloro comes first in the alphabet. So we're actually going to name this as a 3-chloro 2-methylpentane. That would be the full name there. Okay, so 3-chloro 2-methylpentane. We're numbering from the nearer end, the nearest end to the substituent. Over these learning checks now, okay? So I'm going to make my screen just a little bit bigger and we'll write the names down. Let's look at A first. A, let's count the longest chain. 1, 2, 3, 4, 5, 6. So we know our base name is hexane. Now remember, we're going to start counting from the end closest to a substituent group. So it's going to give our branches the lowest numbers possible. So we're going to start counting on this side. 1, 2. So at 2, position 2, we have a methyl, 2-methyl. And at position, here's 3, 4. Position 4, we have another methyl, 4-methyl. That could get really jumbly writing 2-methyl-4-methyl, so we can combine these. We're going to write the positions 2, 4. And because we have 2 of these, we're going to put a di. So di meaning 2, methyl for the group. Because there is nothing else, no other substituents, we just put the base name attached to this now. So this becomes a 2,4-dimethylhexane. When we're talking about B, so let's count B. 1, 2, 3, 4, 5, 6, 7. Our longest chain is 7. That's heptane, because it's all single. Let's count what we have for substituents. We have 3 things. Yes, if we count this way, 1, 2, we hit something on position 3. And if we hit this way, 1, 2, 3, but we hit 2 here. So we're going to count from this side, so where we hit 2 branch points, so we can get them with the low numbers. So here, 1, 2, 3. At position 3, we have a methyl. And at position 3, we have a chloro group. The other group we have here, so this is 3, this would be 4, 5. At position 5, we have another chloro group. Well, just like we did with the methyls up above, we're going to combine these down here. So this becomes a 3,5-dichloro. Now let's look at adding the names together. Now we have to not go by position, but we have to go alphabetically. C comes before M, so C comes first in the name. So we'll write the 3,5-dichloro. Now we'll put in the 3-methyl and then the base name, heptane. So that would be the full name for B. So there they are for you. The big thing when we start talking about those cycloalkanes with substituents, when we name substituents here, if there's only one substituent, we name substituent or the branch is on position 1, and we don't necessarily have to say 1-chlorocyclobutane. We can just go chlorocyclobutane. But if we have 2 or more, we're going to assign carbon 1 to the branch that comes first alphabetically, okay? So that's the key. If we have 2 or more groups, we name and assign the carbon 1 as the one that comes first alphabetically. So in this case here, this is just a methyl cyclobutane. Because this cyclopentane has 2 groups, I have a Br and a Cl. Instead of going Cl then Br, I go alphabetically. So this becomes carbon 1. And then I'm going to number in the direction so my other groups are low numbers as well. So I'm going to go 1, 2, 3, 4, 5. This now is a 1-bromo 2-chlorocyclopentane. If we're taking apart a name and drawing, just remember this 2,4-dimethylhexane. Here, 2 and 4 are the location of the branches. There are 2 CH3 groups at those positions, and hexane means it's the 6th carbon. So let's take apart some names and draw them. The first one is asking you to draw a 3-bromo 1-chlorobutane. The first thing we want to do is go with the base name. Butane means 4 carbons, 1, 2, 3, 4. And we put them in a straight chain because you don't see cyclo in front of it. 1-chloro means on carbon 1. I'm going to just number these carbons 1, 2, 3, 4. On carbon 1 is a chloro group, so I'll put one up here. On carbon 3 is a bromo. Okay. Seeing nothing else in this name, now we're going to fill in the rest of these bonds with what would be hydrogen. So let's just make sure carbon makes 4 bonds. Okay, and then you're going to fill in the rest with hydrogens, and then we can condense it down. This is just kind of showing you the expanded formula. Now let's condense it down. This becomes, we still show that Cl carbon bond, but this is now an H2. CH2, this is a CH with the Br, and then a CH3. It doesn't matter if you draw these on the top, on the side here, or on the bottom. As long as we're in this order, you're all set. Okay, so there again, draw our 4, and then let's make our attachments. Now let's look over here and actually name these. So if we're naming this first one here, this first one is a cyclo, so the base name is cyclo because it's connected. 3 means propane. And because we have a methyl group attached to the top, we're just going to say methyl cyclopropane. Or we could put the 1, but the 1 is understood. Now in this case here we have an ethyl group. 2 carbons is ethyl, 1 is chloro. Okay, so here C comes before E, so we're going to start numbering it this way, 1, 2, 3. So this becomes a 1 chloro, then a 3 ethyl, cyclo, and then it's 6 hexane. You're taking the name and drawing them. And the big thing to remember when we're getting with alkanes in general, the physical state. So alkanes are gases when they're 1 to 4 carbons long. Hence, propane is a gas that you use in a gas grill. There are liquid states when we have 5 to 8 carbons. So when we say a liquid state, we think of the gasoline you put in your car, and we think of octane, right? The octane that's in your gas, well, that's 8. So think of octane for liquid. When we get into solids, any alkane that is 9 to 17 carbons long is usually in a solid form. So there we go, 1 to 4, gas, 5 to 8, liquid, 9 and above, solid. Solubility and density, these are all nonpolar, meaning they're all insoluble in water, and they're less dense, so they float on top, just like we had talked about before. Getting into melting points in this case, and boiling points, alkanes have the lowest melting and boiling points of all organic compounds. They're the base organic compounds, and from here we're going to actually get more intense with more further functional groups on top of them. Because they only have nonpolar bonds between either the carbons or the carbon hydrogens, they have those low melting points and low boiling points. This is just giving you an idea of comparison. And one thing I do want you to know is that the reaction that is preferred by alkanes is known as combustion. So that is going to be the reaction of choice, that we're going to break these bonds through combustion. So because we have a single carbon-carbon bonds, those are difficult to break. They're usually what we call the least reactive group of the organic compounds. They don't really want to react because they're happy as themselves, but they do burn readily in the presence of oxygen. So they will undergo what we call combustion and form carbon dioxide and water. But when we combust, this is like we talked about before, glucose, breaking down some glucose. Here we go. There's the actual balance formula here. And then if we were to balance the equation, just remember when we start balancing any equation, we've done practice on this the last few times, we're going to start balancing so that the number of atoms in the reactants equals the number of atoms in the products. Always start by balancing the carbon first, then going to the hydrogen, and then go back and balance the oxygens. The other elements that you might see in organic compounds sometimes might be, in this case, oxygen, sulfur, nitrogen, phosphorus, or any of the halogens as well. And when we see them in different ball and stick form, they have different colors here. Just know that we'll start talking about these, adding in different groups and different structures. And when we add these atoms in, we might get to different families. This leads us to what we call functional groups. And that these are characteristics and features specific to organic molecules, and they behave in a predictable way. There are certain functional groups that create what we call organic families. So any alkane or organic compound that has what we call this OH molecule or a hydroxide will become and behave like an alcohol. We also have things like aldehydes, ketones. So these are where we're getting into that idea. These functional groups usually replace a hydrogen in an alkane, and they're a way that we can classify families. So here we go. Anytime we're replacing a hydrogen and doing something else. The first functional group we're going to talk about will be actually alkenes, where we replace a hydrogen with a double bond. Then we have alkynes. Aromatics are when we actually, we'll talk about resonance structures back again. Alcohols, thiols, ethers, aldehydes, ketones, carboxylic acids, esters, and then we have amines and amides. So these are all the functional groups that are coming up that we will get into. So here you go, just showing you what they have and what their functional groups are. And we will get into each one of these in depth. Okay, so that's it in the end. If you guys have any questions, as always, please get a hold of me.